name is Princeton. I'm talking on hardness amplification and of predicates and puzzles.
Yep. So thanks everyone for coming. And I guess first I'd like to describe kind of a bit where this talk is going, which is and also to say that throughout the talk you can probe a little bit, but don't probe too deep, because I'm ignoring a lot of epsilons and deltas and notation. The notation, if you want to make stuff precise, kind of blows up in your face. And so I'm sparing you. I'm doing you a favor. So I'll worry about that now. But OK, so kind of the motivation for this is the amplification of cryptographic protocols, like bit commitment. And it works on other stuff besides bit commitment, but I'll just talk about bit commitment today. And kind of to do this, you get to explore fun areas, OK? And one of the fun areas is related to the XOR-Lemma and hardness amplification, just in efficiently samplable predicates. And so after I give the kind of motivating speech, we'll talk about that. And the other area is weakly verifiable predicates, which are kind of like CAPTCHAs and some of the cryptography around those. So we're kind of start with the overview, go into the two sub areas, and then apply it, hopefully, if we get time in the end. So what's bit commitment? It's this cryptographic protocol, and there's some interaction, say, between the sender and the receiver. And at the end of the first round of interaction, the receiver gets a lock, or kind of a bit, but it's locked up, and he's not supposed to be able to see it, right? And later, the sender is going to send him a key, okay? And the key is going to be used to unlock the bit so that the receiver gets the bit. So the idea is I can commit to a bid just like in a sealed envelope, and I can only allow you to open it later. So there's two properties that you really want with these. One is that it should be hiding, okay? So the receiver shouldn't be able to open the bit ahead of time. Otherwise, you could just send the bit. There's no point in creating a whole bunch of mess. And the other is that it should be binding. And that means that the sender shouldn't be able to switch the bit in the middle of it. So if I give you an envelope with my bit in it, I shouldn't be able to swap up another bit in that envelope at a later time. Of course, in physical reality, we can't do this. But if it's just some bits, maybe we can do this. So you want it to be binding. So we'll say that, well, and then here we have this notion of weak cryptographic protocols, where these properties hold, but not all the time. So they sometimes hold, okay? So you can imagine that, so it could be weakly, so we say beta hiding, say beta equals a fifth or something like that. If for every, no, maybe 4/5, I guess, if for every kind of adversarial R here, you get that no matter what R does, he can't reveal the sender's bit ahead of time, except with some probability less than 1. So, I mean, he can always guess it with probability half. Just guesses a bit. So that beta is kind of saying is between 0 and 1. It's saying how much better than random the receiver can do in guessing the sender's bit. And for this talk, we're going to assume that the bit he's committing to is a random bit. So he generates a random bit and then commits to that. And this is always good enough by just XORing it with the bit you care about and publishing the XOR. And then alpha binding. So binding is going to mean the sender can't open it up two ways. If this is kind of their interaction here. So they have some interaction that generated this lock, and that S prime can't output two keys that open up the lock to two different values, right? And he can only do this with probability alpha, which is it's unsecure if he can do this. And so we'll say it's alpha binding if he can only do this probability alpha. So as beta goes to 1, this thing is more secure and more what we want. And as alpha goes to 0, it's more secure and more what we want. Okay.
How should we think of the parameters? Beta to be constant and alpha to be...
Just think of them both as constant. I think. Well, I guess I'll show you that here. So previous work of Levy This is 08. So Levin and Rabin showed that if alpha is less than beta minus polylog n, then you can amplify. And amplify just means then you can get as close to, this is close to 1 and this is close to 0 as you like. Okay, so if there's this gap here that, so I should, if this gap is not too small, then they can amplify it. But so that while this is motivating, the results here aren't super duper exciting. So the more exciting part is, so what we do basically is we get this down to poly n instead of, we get the log out of there. But I think more the point is that the way that they showed this result is by showing that they showed there's two different ways that I can amplify the hardness. One is by just repeating the same thing over and over again. So one idea you could have is, well, I'll run this same protocol. I'll get this guy to commit to the same bit a bunch of times. And then if he wants to reveal a different bit and try to change it, he's got to change all the protocols, because the receiver is going to check that it's valid on all the protocols, not just one. Okay, so this is going to amplify the bindingness, right? But the hiding is going to suffer, right? Because I could try to look at all of them. And the other kind of easy way you could imagine amplifying it is by S committing to a bunch of bits and taking the XOR of them all. Okay, and this is going to make it more hiding intuitively, I guess, because in order to see the bit, he's got to see all the bits and guess them all correctly. Okay, but the hidingness, or the bindingness is going to suffer, because if I want to change it, I only have to change one. Okay, and what they showed is that you can cobble together these two different ideas, and as long as you get this, you can cobble them together in such a way that you get the amplification you want. Okay. But in their paper, they said that they thought they didn't really have the right kind of proof idea. So our idea, we think, is more kind of right in some ways.
So what do you do with the randomness? So the receiver must force the sender to use uniformly independent random bits, right?
So
So for example, when you're allowed to when you ask the sender to commit to the same bit again and again, then he can just keep sending you the same commitment. So you need to force him to use independent randomness. In order to actually get the binding to improve.
Right. So it's interactive. So maybe it could be interactive. So yeah. So you'd have to have something in the protocol so that you're right. So
fairly toss coins.
Well, so you're not assuming. So a lot of there was work before these guys, but that work all assumed kind of semi-honest parties, which would be people that kind of run the protocol correctly, but then try to be malicious with kind of what went on. But yeah, so if you ran it a bunch of times, yeah. So that just shows it's not obvious that it works. So that's that's good, and because these XOR-Lemmas, sometimes they seem obvious, like it should work, but that's an example where it doesn't seem obvious. But if you do things right, it'll work. And the other thing that no one asks is that, why is this the right thing, alpha, some gap between alpha and beta? And the reason it's right is because if beta is less than alpha, then you can then you can't do it. So you can't do it. And but one protocol that almost satisfies that is that some guy he flips a coin, the sender flips a coin, with some probability he sends his bit over, and with some probability neither of them say anything. Okay? And this is kind of in a semi-honest way, this is beta hiding and alpha binding, but you can't imagine trying to amplify this ridiculous protocol to get anything useful out of it. Okay, so that's the motivation, I should say. So today, we'll try to get. Now I'm going to tell you about the cool stuff. I'm not really a crypto guy. Okay, so this XOR-Lemma for efficiently samplable predicates. I spelled that wrong. So the idea here is that we have some predicate P. We're going to make it go to plus minus 1 because I'm hoping that will make my life easier later on. And it has some hardness in it. And we're going to want to amplify the hardness. So, okay, so I should say first, what does efficiently sampleable mean? It means that if I pick a random x, I can figure out what its predicate maps to. So I can generate pairs of x, p of x, where x is random, right? And what the goal is going to be is someone gives me an x, and I want to tell them what p of x is. And these turn out to be different things.
So you don't need to necessarily be able to compute p of x from x in order to sample those pairs, though.
Right, exactly. Exactly. So we're going to use that. So we're assuming that we're going to assume that p is efficiently sampleable. So that means I can always generate these pairs if I like.
So essentially, you are assuming that you have some sort of oracle access to p, where the oracle outputs random samples.
Yeah, a random x and p of x. Definition. I see. P. So we're going to call you delta hard if you can't be predicted more than a 1 plus delta over 2 fraction of the time. Bigger. Okay. Sorry. And of course, the XOR-Lemma says that says stuff like if I take, I want to call this P XOR K. So if I take K inputs, and I make a new predicate that outputs the XOR of them all. Right? Now, I want to say things like that this should be harder here. So that I think, say, you want to say things like if P is 1 minus delta hard is I omitted some epsilons. We want to say things kind of like this.
So hard. Oh.
So each xi is a n-length bit.
Yes. Yeah. Exactly. Exactly.
The lemma says what? That this is true, or is this still part of the definition?
No, this is the definition of delta hard. And the XOR-Lemma says statements that look like this. Okay, I want to leave it a little bit vague right now. And I haven't done these boards before. This seems tricky. Do that. Do that. Okay. And there's two kind of, I would say, main flavors of proofs of this lemma. You're going to taste both flavors today. There's Levin's proof, and then there's this hardcore sets proof. Okay. So how do we prove something like this? How many of you guys have seen the proofs of this before? Everyone? Let's say everyone. Have you seen both of them? Okay, I'll remind you. Okay, so Levin. So this was kind of, the XOR-Lemma, I guess, was conjectured a while back, and people are kind of using it without having, it seems so true that you barely have to prove it, but apparently it took a while for Levin to come up with this proof, and these proofs are slippery. They're all a little slippery.
It was actually, Yao wrote it down and probably had a proof.
But never published it.
Just, likely had a proof at the time, but didn't write it in the paper.
Huh.
And there were other proofs that were around at the time, but not as slick as Levin's.
Oh, okay.
So,
Okay, so I'm going to do this with circuits, not with, so it kind of a non-uniform setting, and just to make life easy. So if assume P is delta hard, well, I'm going to show this statement here. And G is going to be a little character that pops up a lot. And it's a function that goes from 0, 1 to the k to 0, 1, but it's going to be a, I guess, minus 1, 1. And here it's going to be XOR. Okay. In Levin's proof, it's always the XOR. Okay. We'll make it more general and more complicated later. And you use induction. On K, and to show that basically no circuit small, I should say small, can better than. So I'm going to use induction, and the base case is pretty simple, because in the base case I just have one input, okay, and then it's exactly that P is 1 minus delta hard. I'm going to do, yeah, well, it'll be, XOR can just mean multiplication, yeah. And so that when I can take expectations and multiply stuff, and it'll just, then when things get random, they go to 0. And in Levin's proof, it's just really helpful to have these values.
It's a natural way if you're going to do correlation between.
Yeah. Okay, so, say there exists some circuit, small circuit, C, that, such that, use it right here, expectation of C. So it has some nice correlation with XOR and P. Okay. And now I'd like to show that eta is going to be small. And so the trick of this thing is should say, so I'm going to use y to just notate x2 to xk, so the ladder inputs. See if I did this right. Okay, so this by is going to be 1 over 1 minus delta times this expectation here of the circuit evaluated at so you're going to fix the y, which is the ladder inputs, and you're going to take a random first input, and you're going to compute this. Now, this here has to be pretty small, less than 1 over 1 minus delta. 1 minus delta, or between 1 minus delta and delta minus 1, because otherwise this function here would have good correlation with the predicate. And we assume the predicate was small and had no good circuit. And if this worked for any y, then I just plug this y into the circuit, and it'd have a good predictor for p, where I'd put x in the first value and a good predictor for p. So this expectation here has to be between 1 minus delta and delta minus 1. And so if I do this, the value is still between 0 and 1. Okay? So say this is a random circuit that outputs this. It outputs 0 and 1, but it gets this kind of expectation, say. Now we note that 1 minus delta to the k minus 1 expectation over y, v of y times p is 1. And this is by the inductive hypothesis here, because b of y is a circuit, so it shouldn't be able to compute p of y very well. But this just equals the expectation of over x1 of y delta times c of to this is just the thing we want to bound now. This here, the correlation between our circuit and p of x times p of y, because this is just the XOR combining here. And we gained, because we got this 1 over 1 minus delta here, which we can pull out. Okay, and then this we said was less than eta, or greater here. Okay. And so we get eta over 1 minus delta, which means that this implies that eta is less than 1 minus delta to the k, right? Which is exactly what we wanted to show. Okay, now, in all these hardness proofs, there's an algorithm lurking. And so let's kind of look for the algorithm here. It kind of exists. Okay, so what this says is if I'm computing better than I should be, if eta is bigger than it's supposed to be, one of two things happens. Either I can fix a y such that I predict the first value well, right? Or I violated the inductive hypothesis. Okay, if I violated the inductive hypothesis, then just run this algorithm now, but with 1 less k. And sooner or later, I'm going to find an input where I fix the first input, and I fix the last inputs, and it gives me a good algorithm for the first input. Okay, so that's kind of the algorithm, as it were, that you get out of this thing. So this proof is nice because it works. Well, because it's nice, but it only works for XOR. Okay, so and it doesn't give the same. It doesn't have the same like explanatory oomph of the hardcore lemma proof, which I'll show next.
So you have a G up there, which you actually haven't used.
Yeah, right. So G, here it's XOR, but you could imagine G being a threshold function or anything, actually. XOR is the one that's always used. It's kind of the most useful. Sometimes in, not here, but in coding theory, you might want it to be monotone combining function, or if you want a monotone code out, or if you want something like we'll see if you want it to be an extractor. Maybe you want G to be an extractor so that kind of if you have enough randomness in these bits here, I want to get a random bit out. Okay, so I guess can people see, is this board okay to use?
This is good.
Okay. Oops, next page. Okay, so now I'm going to show you the hardcore lemma. And I guess I want to say there's two sides to it. There's kind of the hardness part, and then there's the algorithm part. So the hardness says, you know, if P is delta hard, this means that, this is the lemma, this means that there exists a delta set. A delta set is a delta-sized fraction of the inputs that cannot be predicted better than a half, essentially. You get a little wiggle room. And then you can use this to show that you cannot predict, say, G of P to the K better if okay, so it says that there exists this delta set of inputs that's actually really hard. No algorithm can do better than a half, so that if your input lands in that, it basically looks random to you. So once your input lands in that, and so here, when you do this XOR k times, if any of your inputs land in this hard set, then the output's going to look completely random to you. Okay? And this, so it kind of makes it from this computational hardness here to it gives you a kind of information theoretic hardness statement. It says that if I have some combiner function, so again, think of this as XOR, it could be more general, and I put k values into it, I can't predict this combiner function any better than if each input with probability delta was flipped. Okay. So this looks a little confusing, but it's actually really easy to work with a lot of times. For instance, if G is an extractor and you just need some randomness in each bit, or for the XOR, this is really easy to work with, whereas this is a lot harder to work with here. Okay. And then there's this algorithm side to things. So the algorithm side says if I can predict G, then for every delta set, I can predict the function better than random, and then I can actually predict P better than I'm supposed to. Okay. So again, there's an algorithm kind of lurking in the background, and what do these algorithms look like? Well, this algorithm here is pretty easy. So I'll try to show this. So you say fix an algorithm A. And then we're going to look at this kind of correlation. And then what you're going to do at each step is you're going to replace one of the inputs. So instead of G, which is your combiner function, your XOR, working with P of x1, it's actually going to work with P tilde of x1, which is what? It's random if x belongs to this hard set, and it's whatever it was before otherwise. So, and you keep on doing this until you've replaced all these p's by p tildes. Okay. And now the point is that this here can't be very large. Information theoretically, it's hard because I took this p, and with probability delta, I replaced it by something random. So this g of this thing has a lot of randomness, information theoretically, and so A can't be very closely correlated with it. Okay? But the claim is that all these expectations are equal, right? So if there's not a lot of correlation here, if this is small, then this up here had to be small too. But that's just saying that A wasn't very good at predicting what it was supposed to predict to begin with. Okay? So what happens? Why are these things equal? Well, they're equal because if, let's see, where are we? We're saying if I can, be careful here. If they ever changed, so I fixed, if they ever change, then I can predict P on the set S that I swapped out. All right, if they ever change, the only place they change is on S, so my A somehow figured out that things were changing on S, okay, and it could pick it out. And so the algorithm that you get from this is the way you get an algorithm is you're going to fix your set ahead of time here. That's the set you're swapping out. You want to compute better than random on the set using this algorithm here for G of k. And the way you're going to do it is you're going to fix a lot of all the other inputs are random, so we can just fix them. So we're going to fix all the other inputs and just leave the one that changed, the coordinate that changed, and you're going to put your real x in there, and that's going to compute it on that set. Okay, so the way the algorithm looks, I guess, is this a happy board or not happy board? Okay, is that it A, and then it fixes some x1, and then it puts x in there, and all these guys are fixed. Okay. And now, what does this this function here look like, the hardcore lemma? Well, it's a boosting kind of operation. So it says if you can solve it correctly on any delta set, you can solve it overall. And from delta set, you really just need a distribution with enough entropy that you're solving it better than a half on. And so you're doing this boosting operation. And so it's basically asking for different sets, asking you to do well on different sets, and then it'll basically take the majority of all those things. So in the end, your algorithm, your circuit C that you get to predict your P, is that it asks for all these different sets. And for each set, you gave an algorithm that fixes all the inputs except for one and puts x there, kind of hides x, as it were. But it could hide it in different places and with different other values and one such. Okay. So the point of doing all this is to try to then apply this to our bit commitment here, which was kind of the goal. Okay. So we want to kind of apply this to boosting the hiding of bit commitment. And we see that Levin's proof, Levin style proof actually works. Well, I guess I'll probably show you later. But the XOR proof does not work, right? Because the XOR proof says the hardcore lemma proof says that the way I'm going to take what I want to do here is I want to say that if I run this in parallel a bunch of times, and if I have a receiver that breaks the hiding of it, then I get a receiver that breaks the hiding on just one round of it, right? Okay. But the way that this algorithm worked here is it ran the procedure a bunch of different times, okay, and inserted the real procedure in different places, okay, and then tries to take the majority. Well, you know, you can't run this protocol more than once because the other guy is going to notice, you know, and it's not even clear, like, what if your guy said to do different things and, you know, these different things and the majority, what does that even mean? And so this won't work at all, okay? This won't work at all. Levin's proof actually does work, and the reason is you're fixing a prefix, and then you're putting it in one place, and then you're running the rest of it. So you only put it in one place in Levin's proof. You got to put it in many places in this proof. Okay. So, good. Time's going well. Okay. So, I hope it wasn't too boring reviewing that stuff, but now our proof kind of combines these two ideas in a weird way. But I mean, you got to, I don't know. I don't want to knock the hardcore lemma because, come on, that's really neat, right? That there's just one set that's hard for all circuits tells you a lot about what's going on. Okay, so I guess I'll try here. First, I should say. So, you notice that all these things have this goofy thing in it, like this is the B of Y, which, like, what's that? And this has this, like, weird product there. So ours has a goofy thing, too. So think of C of X BR. This is a circuit. This is randomness that it takes. This is the X it's trying to figure out. And it's trying to distinguish between two cases. One is that P of X equals B, and the other is that P of X does not equal B. So it's trying to say, did I put the right answer in here, yes or no? That's kind of what the circuit is trying to do. So that's kind of a way to think about how this is going to be used. So I don't want to write all this stuff. P's are predicate, and there exists an algorithm gen that has input. You input into it the C of X R B and epsilon greater than 0, and it outputs Q and S and delta. Delta, that's a real number, and Q and S are circuits. And what are these circuits supposed to do? Well, S is named because it's a set. It outputs a set. So you give it X and the predicate evaluated X, and it recognizes a set which we'll call S star. And important, it's a delta set, so it's kind of a large set that it recognizes. Okay, and I'll explain why we're doing this goofy stuff in a second. was indistinguishability for S star. This circuit that we input is really lousy at telling you what's going on. This should, oh, I see. Okay, so if we swap out p of x and we just flip it whenever x is an s, okay? So instead of getting it the right answer, we give it the wrong answer. It doesn't distinguish this case on the whole thing of S. So S is supposed to be a large set where a circuit is kind of not doing a good job at distinguishing whether or not I'm giving it the right or the wrong answer. Okay.
So this notion of large, so this definition for large set, I mean, this is where you're going to use the samplability of the pairs x, p of x?
Okay,
I'm just...
We'll use it. There's one more thing that I didn't. The last thing that you want is prediction. And this says that Q predicts P well, so I'll just write down the... Okay, and this says that kind of Q delta predicts P. So what's happening here is I'm giving you two pieces of evidence. One is a set on which this algorithm, this circuit C does stinky, and I tell you this set is of size delta, okay? And delta is the right size because actually I can use C to compute a circuit Q that delta predicts P on anything that's not in this delta set, right? Because I get 1 minus delta over 2, so in the set I'm random, and outside of the set I always get it right. Okay, so delta is the value for which I can actually do this.
So you haven't said that Q only fails on S star, basically.
I haven't said that, but it's true. But that's going to happen, yeah. So people, so this is just a way of, I don't know, it's a way of saying kind of what's going on. Though one thing that's different in the hardcore lemma is that our hard set S depends on the circuit. It's not for all circuits, it depends on our particular circuit.
P, the predicate is also, I mean, do you construct the predicate or the
No, the predicate's given to you.
Q is a predicate as well?
No, Q is a circuit. These are. So my algorithm takes in this circuit C and produces two circuits. One's a circuit that just recognizes a set, and the other is a circuit that tries to predict P.
So this algorithm has to figure out how well C is actually doing.
Yeah, exactly. Exactly.
And figure out where it's making its mistakes.
Right. So, what am I going to?
The left side of that is erasable.
The Levin stuff,
Well,
or
the
this
left side is-
XOR stuff. Yeah. Okay. Good point. Thanks. Ooh, nice eraser.
going
S is not dependent on, well, just the size of it is, because Q is supposed to be predicting P in a large fraction area, and where it's not is of size delta over 2. But in order to fail in delta over 2, you really have to fail in delta, because you're predicting it randomly in this set here. And that delta set, I'm going to kind of claim, that's kind of S. So S is kind of a witness to where C stinks on predicting P. S star, where, well, it's where Q does, but it's also, because Q's baked from C, it's kind of where C fails also.
Yeah, actually, yeah, in the formality and indistinguishability, S takes both X and P of X. So it's P of X XOR X, comma.
P of X, yeah. Okay, so the proof is really not so hard once you get your head around it. So I'm going to find delta X equal to kind of, I guess, the expectation over R of so how well does our algorithm do on a particular X, right? Yeah. Yeah. This is like minus P here.
Oh, okay.
And I should close the expectation there. Okay. And then I'm going to order the X's based on their delta X. Minus P. So this is where it gets the right answer, and this is when it gets the wrong answer. It's saying, I mean, because your C could just output 1 all the time. I mean, I said it's supposed to distinguish these things, but who knows? So this is how well it distinguishes it on a particular X. Okay. And now I'm going to map. So I'm going to put these in order. So the big ones are going to go here, and the small ones are going to go there. So this is just 0, 1 to the n, but I've ordered them by delta X. And they're all between 1 and minus 1. And it's some line, okay? So what is our S? So first I'll tell you kind of ideally what it is. And our S is going to be, we're going to look, and we're going to go back this way until the area under the curve here and the area above the curve here, say there, are equal, okay? And then this portion here is going to be our S, okay? And there's some X naught where it transitions in this ordering. And this is going to be delta X naught here. And so what is our Q going to do? Our Q is going to compute delta X. It can't compute delta X, but it can compute it up to a plus or minus. Okay? And if it's above delta X naught, it's going to use whatever prediction C output. Okay? And if it's below delta X naught, then it's going to randomly round it. So what I mean by randomly round, if it's 0, it'll be a half. If it's like here, it'll go here with 70%, 75% probability, and there with 25% probability. So it gets the expectation right. Okay. Okay. So, and I'm going to claim that this will satisfy those 3 properties up there. Right. But the only thing this depends, if I put a 1 here and a minus 1 there, or a 1 here and a minus 1 there, the only thing that flips is the sign. Right? So I can compute it up to an absolute value. right? I compute its absolute value. Okay, but so then what I'm saying is that C has a prediction. So if I put 1 here and -1 there, and this value is positive, then C kind of thinks it ought to be 1. And if I put -1 here and 1 there, then C thinks it ought to be 0. Right? So C is kind of voting here, okay, right? And if it votes really heavily one way above delta x naught, I'm going to pick that direction. And otherwise, I'm going to randomly round it between delta x and minus delta x. Okay. People see what's going on here? So this is exactly what Levin's doing, right? In this kind of multiplying by delta x naught, this is like the multiplying by 1 over 1 minus delta. Boosting there. Okay, but note that this satisfies, S is a delta set because we just output delta to be the size of S. Okay, it's indistinguishable for things in here because in here I'm doing this randomized rounding, and the randomized rounding is exactly chosen so that this is chosen so that these areas are the same. So when I randomly round, I get these wrong with some probability, but with the same probability I get these right. I get kind of advantage of these getting right, and so they cancel each other out, and so I do at least random on the set S. Okay, that's what we need. If you do things that are less intelligent, you do worse than random on set S. We just need to do random on the set S.
Yeah, this is actually the set S.
Star, yeah. And then our Q algorithm always gets things right when they're past x naught, which is a 1 minus delta fraction of the time, right? So it gets it right 1 minus delta fraction, random on a delta fraction, so overall its prediction is 1 minus delta over 2. Okay. Okay, so do people kind of, so in reality, you can't compute all these things in this nice curve, so, but it's not so hard to do this. So I'll just rush by some details so that but what you do is instead of using all the randomness, you just pick out a few, you subsample some randomness, and then you run it exhaustively on these samples. And this creates kind of a new ordering over these things, but you can actually compute the ordering exactly. And then to find x naught, you just sample a bunch of possible x naughts, and you ask if this, if it's indistinguishable for that x naught, and you'll find one. If you sample enough, you'll find this guy, and you can compute delta of it, so you have everything you need just with some, well, to compute that value there, you have to sample more things less than it, but you can do that. You compute everything really accurately, and it works out.
So if delta is really small and these elements are really rare,
if this delta is really small, so I think I omitted some fudge fact. If delta is really small, see, then the set can just be the whole thing essentially. There's yeah.
So with the region where the curve is close to 0, it's where C is sort of indecisive, right?
Right.
So how do you know that? How do you know that that this is not the case most of the time?
It can be the case most of the time. In fact, from the XOR-Lemma, I would expect that it is the case most of the time. We just can't show it. That basically it should go here, and then it should drop down to 0, and then go there. That's what you'd expect.
You know that it's indecisive only in a hardcore set, right?
Well, but what I'm doing is my algorithm outputs how indecisive, the delta is kind of how indecisive C is. So if you give me a really indecisive C, I'll output a large delta. It doesn't mean that the function's hard. It means that this circuit doesn't give me any information.
You compare yourself onto the performance of C. So
Yeah, exactly.
So if C is good, you can do not much worse by these two circuits, S and Q.
Yeah, if C is good, then Q will be good, and if C stinks, then Q will stink, but we'll get a large set that fools C.
So now might be a good time for a 5-minute break?
Actually, can I Can I go for another 5 minutes? And then, okay, so this was not what we wanted. Because we wanted one of these XOR lemmas, and I gave you something, but it only works for one input, right? So we want something that works for kind of k inputs, right? So, we'll go over here, do it for k inputs. So, and okay, so this is, right. So this part is going to look a lot like the hardcore lemma kind of proof. We have two experiments. Experiment 1. So this is what's supposed to happen. Okay. Okay. So now our C input takes many inputs, and well, it's going to try to distinguish. The thinking is it's going to try to distinguish if P, where's my C again? Now, C of K distinguishes, can't spell, if P G of P of x1 right. So G is our combiner function, and it's trying to distinguish if I combine with G the real values of the P if I get the same thing as if I combine the alleged values of P of x. Okay. So that's, think that's what C is supposed to do here. And experiment 2, I owe you more notation. I see. Okay, so experiment does what it's supposed to. Experiment 2 does something slightly different. So it takes the prefix and outputs this of what's happened before, and outputs this SI star that I haven't told you about. Okay, but the point is that SI star depends on the prefix that was chosen, and then it gets an X, and if the X is in the hardcore set for that thing, it flips its value, and if it's not in the hardcore set, then it outputs the correct thing, and it outputs what the circuit says on this. Okay, and so the idea, I'll write a theorem in a second, but the idea here is that at each step, I probably just erased. Yeah. It's the same thing as is happening here. At each step, I fix a prefix, and then for this particular guy, I'm going to swap out a set. And then for this next guy, I don't have more than 2 guys there, I'm going to swap out a set. And then for the next guy, I'm going to swap out a set. And each time I swap out a delta set, this S star that I generated. And so by the end, I've swapped out all the sets, and I output C of Bi to Bk. But these Bi's and Bk's are not all what they're supposed to be, because if they're in any of these delta sets, then they're random. Okay, so if they're in one of the delta sets, they'll be random. But what delta set I chose depended on all the things that went before it. But the theorem is going to say that these experiments here output the same thing. Okay, so that my circuit can't really distinguish when I'm giving it the right stuff and when I'm flipping stuff with probability delta, and that's going to give us the same hardcore lemma thing.
Okay, so let's take
Break.
a break now.
Okay.
In 5 minutes. So
This is our theorem then for the k things. So we take as input our predictor circuit and some parameter epsilon, and okay. Well, we produce 2 circuits, and one takes as input the circuit predictor and outputs this q, which is a predictor, and delta, just as before. And the other is creating these sets, but now we need more sets, right? Because we need a set for each prefix. And so it takes as input the circuit and a prefix and the parameter, and outputs the hardcore set there. Okay. And then the claim is that with really good probability, all these sets that I produced are actually large, so I could fool it all the time, right? Experiment 1 and experiment 2 are indistinguishable, that's the kind of conversion from if they're indistinguishable, then it says that kind of computationally is the same thing as information theoretic. So if it's information theoretically hard, it must be computationally hard. Okay, and 3 is that Q predicts well. So it predicts except for on these delta sets. Okay, and so how does the proof just really uses this here. So what you do is you pick a lot of random TI that you run this experiment on, and you take the best Q that you find, right? You take the smallest delta you ever get, and that gives you your Q and your delta, and you ran it a bunch of times, and they were all random. So then the chance that you're going to encounter any prefix that you fail on worse than this is small, right? So you run it enough times that chance you encounter in running of experiment 2 something bad is small. Okay. And if you don't encounter anything bad, then these experiments are going to output the same thing. They're going to be indistinguishable for the same reason, because of just because of this here with the set. Nothing changed when I flipped the bit. On the circuit, the circuit that I'm using when I'm showing this thing here, the circuit is not this one circuit, it's the big circuit, but where I plug in the prefix, I fix the prefix, then I plug in the x that I plug in is the next x, and then I randomly fill in the rest of them. That's the kind of circuit that I'm fooling. and it says that there's a delta set there that I can swap without this thing noticing, right? And that's exactly what I need to do to get this kind of this chain argument. The kind of there's only one thing being swapped, so that's the kind of what's being swapped is the circuit that I'm looking at, and so I just plug that into here and I use this S.
So at the ith step of this, you're sort of doing that same procedure of figuring out what the delta would be for that prefix.
Yep,
and
exactly.
Figuring out the set for that particular prefix.
Right.
You're doing that over and over again. And
yes. Right. And every time we're doing this, this is where the sampling is coming in, because every time I make this graph, right, I'm sampling tons of stuff. I need it to be, this is not, some papers, not ours, try to improve the efficiency of the number of times you have to sample things, because if you're doing things when you don't have efficiently sampleable predicates in a different setting, it matters. We're not doing that. This is very inefficient in the number of samples you take. Okay, and so does this make sense to people? All right, and then the claim is that this technique, unlike the hardcore lemma, does generalize to the cryptographic setting. Because what's the algorithm? How am I generating the algorithm? I'm just taking a bunch of prefixes, and I'm trying to find one where the next guy is a good predictor of what it actually is. That's all my Q is here. All I did to design Q was I picked a bunch of random prefixes and saw if it predicted if the next one did well on the next one, right? And so that's all my kind of distinguisher does, and so if I have this big cryptographic thing, I can do that. What I do is I don't have any good pictures here. What I would do is I would simulate it for some prefix, and then I would test to see if if plugging something real into the next one is a good predictor. Okay? And if it is, I stop there. And my algorithm is I simulate it up to that round with those prefixes. I remembered all the memory. And then I run the real guy. And then after that, I continue simulating it. Okay? And I'm supposed to be, because Q does well, then I'll be able to predict this thing. So I should maybe, do I have any? I want to write this down a little bit more because I'm seeing confused heads. So Levin can go, yeah. Okay, so now I'll tell you what C of K is. So there's a bit of a notational kerfluffle here. So we have two different B's floating around at this point, which is unfortunate. There's the B from the predicate. Well, I'll tell you in a second. So and P of X is so the idea is that X here is supposed to be the randomness input to the sender. Okay? So X has in it what B is, right? Which is why this is B1 prime. Okay? The randomness of the sender determines what bit it's committing to. Okay? So this X encodes the randomness and the bit. So the randomness uses and its bit are both coming from X here. Okay? This bit here is the bit that we're going to give our circuit, and it's going to try to tell us if it's the correct bit from this or not. Okay.
That's a prime there? That bit is primed?
Yeah, that bit is primed. This one here.
So
Okay.
B1 prime is kind of the guess to what B1 is.
Yeah, B1 prime exactly is a guess. So then we have this receiver, our malicious receiver here, and we're building this circuit based on our malicious receiver, and he interacts with S, right, on S's randomness, okay, and he outputs something, and what he outputs is supposed to be the guess of what G, which is our combiner function, applied to all these BI's is, okay? And then we're asking what's kind of the correlation, as it were, between that and G applied to all the kind of, said that maybe this is true, maybe this is true. We're trying to see if he can distinguish the difference. This is why we build C to kind of try to distinguish these differences, okay? And right, and P of X is, kind of the right commitment. So if we look at experiment 1 and experiment 2 here, in experiment 2, the claim is that you plug this circuit into our theorem, right? And it says that experiment 1 and experiment 2 are different except for this delta difference. The delta difference is what you can predict on, so you can break it with delta, with probably 1 minus delta over 2, and otherwise you get this equivalence of these experiments where these sets that we're flipping are of size delta. Okay? And what does it mean that these experiments are equivalent? Well, this experiment, so this experiment here, you can't possibly predict that, because here, what this is, computing, is this thing up here, but this part here actually has a ton of randomness in it because these bits are flipped with some probability, right? So if G is kind of an XOR or something like this part here has a lot of randomness in it, and so the expectation of this is going to be small and not tell you a lot about what's going on. Okay, and so this is kind of the information theoretic hardness here, and relating it to the computational hardness here, and the claim is that the kind of this here tells you, this circuit tells you kind of how well you're doing. So it's a little hand wavy, but I hope it gives you a good idea for what's going on. Okay, so right. So that's amplifying the hiding of the bit commitment protocols. So now what can we do with the binding? Well, it turns out this relates to these weakly verifiable predicates. So a weakly verifiable predicate is something like a CAPTCHA, where you have someone who randomly generates a puzzle and a checker. He sends the puzzle to someone else. The person sends him back an answer. Okay. And this guy checks if the answer is correct or not. So the point is that the guy who's trying to solve the puzzle doesn't have the checker available. He can't check it himself. So like a CAPTCHA, there's some like words that are maybe hidden in it. This guy remembers the words and checks if they're going to be the same, but he doesn't send the checker over to this guy. This guy just gets the image. Okay. So these have been looked at before, so let's see, Canetti, Halevi, and Steiner in 2005 showed an XOR-Lemma, basically, for these. That if it's hard to do one, then it kind of the hardness exponentiates down if you want to do all of them. And then Impagliazzo, Jaiswal, and Cabinets in 2009 showed threshold hardness, so that, and one of the ideas is, well, maybe even people get CAPTCHAs wrong sometimes, so maybe we don't want to require them to all be correctly. We want some threshold and say that, you know, people should be able to get them 90% correct and computers only 80% correct, and we want to say that, you know, there's some division here. And this was strengthened by Jutla, and he improved it to be equal to kind of a Chernoff bound. So what we show is that if G is any monotone function, I think we show what it should be. That if G is any monotone function, I guess I need some notation, so ignore this notation over here. I can't read what I wrote. So y is what the sender outputs, or the solver outputs. So it's kind of his solution. Gamma is the kind of checker that the puzzler outputs, and it's saying, did I do it correctly? This is the success probability. So I guess. And then the theorem says that, I'll get rid of. Here, what information theoretic hardness should be is kind of easier to state, which is nice. This algorithm gen, I guess, of C, G, epsilon, delta, n, that takes all these as inputs and outputs circuit D. This is a circuit such that, so C, this is it. This probability. So if I have some C that does well on this combined function, then I can do well on an individual one too. Oh. Okay, so I didn't manage to get all the epsilons and deltas out of here. So if, okay, so this delta G is, G's are what? Gamma, thank you. This gamma G, G's are kind of combiner function, so it could be a threshold function that evaluates to 1 if you get half of them correct. It has to be monotone, as I said before. It could be, you got to get them all correct. These are the cases that people solved before. They're the interesting cases, you know. People really care about, but it could be anything here. Then the challenger interacts with the prover, the circuit interacts with the prover, sorry, and it gets 1 with some probability, and the probability that gets 1 is you take your G, and in each place independently you put 1 with probability delta, right? Because he's kind of breaking it with probability delta, so you put 1 there with probability delta independently, right? So if he beats that, if he does better than independently, so maybe there's some correlation or something like that, he says, well, there's not correlation because I can take any circuit that does this, and I can actually beat delta on just one instance. So the only way that you can beat kind of doing it, so you can't beat doing it independently, right? If you can do better than independence, it's because you can actually do better. Okay, so this is nice because this is really easy to state. Like this is kind of the right bound to stick in there. Okay, and the monotone condition is necessary, okay, because it doesn't make sense without it, for one. But yeah, exactly. I mean, because but in the previous case, you actually can't try to fail. Right? In the previous case, when you have Boolean values, like random's random. You can't you can't fail if you want to. But here you can. And so if you just take like if G of B is 1 minus B, then this doesn't work. So, but that's kind of to be expected. Okay. So so all that's I need to do. Okay. So previous works are have more better ideas in them than ours, but our work is simple. But unfortunately, it's a little messy. So I think I will explain to you what's going on. I will tell you why it's true, and then if you want, it's really a page of algebraic manipulations to show that it's true. Nothing happens in them, but you'll have to take my word for that or look at it yourself. Okay, so how are we going to show this? Well, we want to introduce an algorithm that's going to take this C and massage it into this D. Okay, so so I'm going to do this. You do induction on K, no surprise. Okay, so if K equals 1, you output C. Okay, and no big surprise. You can check. G has 3 options. It can be the identity. It can be all 1. It can be all 0. They all work. Okay. So to do more than this, we need some notation. And actually, my claim is that this notation is where it's at. I mean, once you have the right things that you're dealing with, you're pretty well set. You just have to do some ugly manipulations. So G of B is such a weird thing. So what you do is you take in K inputs, you ignore the first one, and then you see if G evaluates correctly using B for the first one and all the rest of them the same.
That's a common, not a 1.
Yeah. Okay, so G naught is a subset of G1. Oh, this notation here, I just want to, I'm drawing each coordinate independently. It's 1 with probability delta, 0 with probability 1 minus delta. That's the notation I'm using there. Let's see, more notation. C. This is more the important notation. This is not. CI is kind of if you got the ith one correct. And pi I is the randomness of the puzzler for ith instance. Oops, I should write bigger. And then the other kind of important value is this S pi star B. Okay, so the surplus, this S I would call the surplus, and it's kind of how much better you do than you're supposed to is kind of the way to think of it. But here, we do something really weird. We ignore we put B, so this B is either 0 or 1. So you ignore the first input, and you either assume you got it right or assume you got it wrong, and you just worry about the other inputs. But we're fixing the randomness of the first instance. So we fix the randomness of the first instance. We decide whether or not we got the first instance right or wrong, and then you carry on, and you want to know if you did better than you're supposed to or worse than you're supposed to here.
You're supposed to mean it. So if you pick a random thing, if you've just got random success with probability delta.
Yeah, yeah.
So you did better than you would have
if you were just doing it independently. So the point is, this will be the point of this. Whenever we have surplus, we can induct. Okay? Whenever you have large surplus, you can just do induction, and now you made your K1 smaller, you fixed the randomness of the first guy, and you only have K minus 1 inputs really to concern yourself with. So that's, and the other point is that because you fixed B and you fixed pi, these are the two things that you actually need to fix that aren't going to be important, so that you don't get this exponential blow up, right? Because a lot of times in these arguments, you need to, well, we'll see, but you need to fix things two different ways, and here you don't. Because if you have surplus with pi and B, you can just carry on with disregarding everything else. What did I have here? Yeah. Okay, I'll go to this board over here. Okay, so I gave you the setup, and now I need to tell you what the algorithm does when k is larger than 1. So it does this. It picks many pi stars, and simulates to estimate. Well, let's not just worry about estimating. Let's just say we compute it exactly. S pi star 1 and S pi star 0 and S pi star 1. Okay. So it does this for a lot of different things. It tries to estimate it, and it's trying to find some surplus so that it can induct, right?
So pi k is the...
This is star, sorry. It just picks many different trials of randomness for the first round and tries to simulate this. Okay. Now there's kind of two cases. I see. Say this set. Wait a second. Yeah. I think this should be. Wait a second. Oh, I have too many C's here. That's... I think I just copied it wrong. That's B, B1, and okay. So if I did well, then I'm going to use induction on the theorem, and I'm going to generate G. I'm going to use this gen, and I claim that I have one less input. So my circuit is C prime. C prime simulates with simulates P1 with C, and then follows P of G prime. So P of G prime now is k less than 1, so we use inductive hypothesis there. G is just what you think it should be. You plug in B1, this B, to where B1 was in the normal G, and you take G prime, and then you adjust your epsilon and your delta and your n all stay the same. So you just kind of push the problem further on. Next case is the interesting one. Well, interesting one to analyze, I guess. So here you don't have So you used to have at least epsilon surplus, which is why we're in this thing, and now you don't have so much surplus. You have slightly less surplus than you have before with all these things, and you output D of C, and what does this do? That phase 1, so in the first thing, you use phase 1 to simulate with P1. This is your actual input, the real McCoy, as it were. And in phase 2, you simulate k minus 1 interactions with P1 to get these k guesses, and then I should have. So here's where kind of the magic happens. Okay. So I simulate on the first stage, I simulate the real input, okay? And then I do more simulations, and I get the output of my circuit, okay? And then I test whether or not the ladder values, which I know, right? Because I created these. So this was the real simulation, but the rest of them, I was playing both parts. So I have the checker, right? So I check C2 to CK, and I look and I see whether or not that's in G1/G0. Okay. So G1/G0, these are cases where in reality I live only if I do well only if I got the first input right. Otherwise I do poorly. Okay. So if I'm in this case here, that means the first input actually matters. Okay. And so I pick all these ladder ones and I wait for the first case to actually matter. And when it does, I output that answer.
Output answer to what I meant?
I output y1. So I simulated with the real guy. Okay. So I have this guy that runs k different. It runs at k times and outputs an answer for all k times. Okay. So I simulate with the real guy running the first time. Then I simulate the puzzle for the second, third, fourth, up to the kth time. Okay. Now, now I get my output, y1 to yk, that my thing gave me. Okay. And I check how many of the cases 2 through k I got correct. I can check these. And I check if this kind of vector here is in G1/G0. Does the first case matter, given the fact that I got these other cases correct? Okay? And if it does matter, I output what it gave me. And if it doesn't matter, then I run these, then I kind of go back, forget what I did, except for this part. I can't forget this part because this really happened, right? And I go back and I try k minus 1 more simulations. And I see if I'm in this set again.
And so why do you not just keep doing this over and over again?
Right. So you could, and you just give up at some point.
Why would you expect it to happen reasonably?
Why would you expect? Right. So the reason that you would expect to have, so let me just, yeah. So it's a really hand-wavy explanation, but the reason is because you used to have these surpluses. You used to have nice, healthy surpluses, and then of epsilon, right? And then you got to this case here where you couldn't find anything with a good surplus. And what that means is that kind of before you're doing really well, you're predicting things really well, and now all of a sudden, things aren't working out well for you. What this means is that your first variable actually has a lot of goodness in it, right? And okay, so, but there's a couple things that could go wrong. One of them, as Paul says, that this never terminates. And why is that? In the mathematical computations, it doesn't matter. Like because the people that are, the inputs that are contributing to this happening badly, they're not helping you in creating the surplus that's big, and so you can just kind of ignore them. I mean, obviously they don't, they kind of, but that's kind of the individual, like, these guys are not helping you anyhow. They're not making any difference. They weren't contributing to that surplus. And you're winning because of the surplus. So you're going to win on other guys, but not this guy, right? That's kind of, is that, but the math made sense to me at one time when I puzzled it out and wrote it down. And but even then it was pretty wishy-washy. And the reason it works is because algebra works. And you can kind of puzzle out why some things matter and not if you look at it. But I don't have a great, in particular that question is one that is just like, wow, okay, this works. All right, okay, so okay, so that, I guess, so that's this, but yeah, so that was my hand-wavy kind of proof. You don't want the real proof, trust me, but it's kind of, I think it's kind of neat because people had written papers about it before, and this is kind of a way to do it with conditional probabilities and nothing else. But the other neat thing is that it applies to these bit commitment protocols. So I think I can do this in the last 10 minutes, but let me erase this thing here. I'll just do this here. So I guess in cryptography, this is a kind of standard trick I wasn't aware of. So we have our weak protocol. And we'd like to amplify it, right? So So we're going to execute it. And then we're going to use this, I guess, circuit that Valiant came up with, and independently some other people in 84. And it's a kind of monotone read once circuit. I guess we'll call it and it kind of works as a threshold circuit. Oh boy, beta, this should be alpha then. Okay. So that if you put inputs that are beta, that are 1 with probability beta, then it always outputs 1. And if you do it only with probability alpha, then it never outputs 1. So it's kind of, and it's this monotone thing. And the claim is that we're going to use this circuit to, in a black box way, boost our bit commitment protocol to a strong one. Let's see. Oh, shadow. Okay, so so we have G as above for alpha, beta. This is binding, hiding, and K. And the sender commits to CI in instance I, okay? And then we have additional variables. CI plus 1 to C2K minus 1 that correspond to the gates. And if it's an OR gate, then CL, if L is an OR gate, then CL equals CI XOR CJ, where these are the input wires. And if it's an AND gate, then CL is random, and publish CI XOR CL and CJ XOR CL. And now, so you run this, you commit to the inputs, and then to open it, the sender sends all information. But the bit that was actually committed to, I should have said that before, is the output of the circuit. Okay. So the bit I committed to is output of the circuit. And now I kind of want to try to convince you in 3 minutes, maybe it'll be saved by the bell, that that this works. Okay, so if I think of the think of the inputs to the circuit being, for the hiding, think of the inputs to the circuit being 1 if he 0 if he breaks it, and 1 otherwise. Okay. Then if the circuit the claim is if the circuit evaluates to let's do this part here. So if it's an OR gate, then to get this value here, he had to break both of them. So it's really kind of an AND gate to him, okay? But because all the values are negated, it's a it's a OR gate, right? Because he has zeros when he does well and ones when he does poorly. So it kind of reverses everything and changes ANDs into ORs. And so if he doesn't, and so if he has, if either of these is,
It's hidden,
then they're both hidden, yeah. So I guess it's a way to say it is that it's 1 if they're hidden,
Yeah.
and 0 if they're not hidden. So, okay. And then, pardon? Okay.
And the AND gate,
The AND gate, if I know either of these, then I get this guy. Oh, I see. So if, yeah.
so in this case, you want it to be hidden if
Both of
are
them hidden.
So you've published those things.
I see. Well, okay. So I think I'm out of time, and I'll stop here rather than drag on. But this is kind of the idea of how this proof works and how you combine the XOR-Lemma and the weakly verifiable puzzle stuff together.
Okay.
So
Well,
thanks so
good.
much.
We can discuss over lunch.
Yes.